Okay, so now let's look at different types of interpolation. All right, so the types of interpolation have to do with essentially what class of functions you're going to look for. It's like this G, it's like which approximates or interpolates f to b in. Okay, so the first type has to do with, say, polynomials. Okay, so you could do polynomial interpolation. Instead of polynomials, you can also sort of look at things which are only piecewise polynomial. Okay. So these are what are called, sometimes referred to as splines. Okay. You can interpolate, instead of using polynomials, you can look at sort of quotients of polynomials, which are rational functions. You can also look at trigonometric functions. So this is associated to things like the Fourier transform and Fourier transforms. Okay, and then other classes of functions include things like exponentials. So those are sort of some of the main types of them. And they have the property usually that they're easy to work with in some precise sense. Okay, and the other thing you care about is their approximation power, to what extent they are able to approximate the functions which you're working with. Okay, so I'm going to start by looking at polynomial interpolation, and then the natural question to ask there is, why polynomials, right? So okay, so let's look at polynomial interpolation. And the first question is, why polynomials? Okay, so a polynomial, so I'm looking for a g of x, which is some polynomial of finite degree, say a0 plus a1x all the way up to an x to the n. So one of the reasons why polynomials are nice to work with are that their derivatives and integrals are easy to compute. So they're still polynomials, amongst other things, right? So derivatives and integrals are easy to compute. And they're still polynomials. Okay. The other thing is that they're efficient to evaluate. Okay. So that requires a little bit of comment. Okay. So let me just write this statement down, and then I'll say what I mean. So okay. So if you naively try to evaluate this polynomial, then you're going to say take 10 multipliers to evaluate this term, n minus 1, it's like to evaluate the next term all the way down to 0. So you have the sum 0 to n multiplies, okay, which is of the order of n squared over 2, right, n plus 1 over 2. So the number of multipliers, if you naively try to evaluate a polynomial term by term, is of the order of n squared. So that doesn't sound too efficient, right? But there is a simple observation which makes it much more efficient to evaluate a polynomial. And intuitively, it just has to do with the observation that x to the n is equal to x times x to the n minus 1, right? So yes, you have to compute this x to the n, but you also have to compute an x to the n minus 1. So if you somehow store that and use that in a simple way, then you don't actually need this order n squared multiplications in order to evaluate a polynomial of degree n. Okay? And so this leads to what is called Horner's method. Okay, so I have this original equation, so I can write g of x in the following way. So I take a0, okay, so a0, if I take a0 out, I'm left with something which has a common factor of x in all the terms. So I'm going to factor that x out. So a0 plus x, whatever is left, a1, okay, a1 all the way up to a sub n, x to the n minus 1, right? So if I leave a1, then whatever is, if I take out the a1 now, whatever is left over, a2 and so on, again has a common factor of x in it. Okay, so I can factor that out again. So plus x times a2 and so on, right, plus x times a bunch of stuff, right? So again, the upshot, if you will, is that if you if you do it this way, you end up in a situation where you only need order n multiplies in order to evaluate a polynomial of degree n, instead of this order n squared number of multiplies, which you would if you had sort of naively tried to evaluate every term on its own. Okay? All right. So, okay, so that's sort of one reason to consider polynomials, that the derivatives and integrals are easy to compute and they stay in the class of polynomials. And the second, which is that if you are smart about it, then polynomials are also very, very efficient to evaluate. Okay, so the other thing, it's like, as we alluded to, is that you want the space of functions you're working with, in this case polynomials, to have to be able to somehow approximate the functions which you're working with in some way. So let me state a theorem, which is the Weierstrass approximation theorem, which makes that statement a little bit more precise. Okay. All right. So the theorem is as follows. The Weierstrass approximation theorem. And what it says is the following, that if you have a function f which is continuous in some interval, closed interval from a to b, then if I'm given some epsilon greater than 0, then there exists a polynomial p such that the following is true, that the difference pointwise between f and p is less than epsilon for all x in the interval from a to b. Okay? So that's a pretty powerful statement. That's saying that if I allow myself to have a little bit of error pointwise, right, then I can always find a polynomial which approximates a given continuous function, right, over the entire interval with error less than epsilon at any point on the interval. Okay. All right. So that you know, at least it's, I guess, one hope to believe that polynomials can be a good choice for approximating functions. Okay. So as a special case of this, right, we have the Taylor polynomial. Right. So f of x is Pn of x, sum from k equals to 0 to n of kth derivative of f at point x0 divided by k factorial x minus x0 to the kth power. All right. So if you're paying attention, then you'll immediately realize that this special case doesn't really help you in proving the Weierstrass approximation theorem, right? Because it's like here, f is only assumed to be continuous, right? So you can't really, improve the quality of the approximation by looking at higher order terms in the Taylor polynomial, because you're not necessarily allowed to take derivatives. Okay, so I should just remark that the standard proof of the Weierstrass approximation theorem is not via Taylor polynomials, but it's through what are called the Bernstein polynomials. Okay, so there is a proof of this result. It's like using it's like a construction that's like associated with what are called Bernstein polynomials. So I'm not going to prove this, all right? But anyway, it's nevertheless it's important to observe that such a polynomial exists, right? And it can be constructed. All right. Anyhow, so instead we're going to look at it's like things which sort of look like Taylor polynomials. It's like and we'll see what I mean by that in a little bit. Okay. So I should observe that we're going to look at what are called Lagrange, it's like, and Newton, it's like interpolating polynomials. So we're going to consider Lagrange and Newton interpolating polynomials. Right, and in particular, the Newton type interpolating polynomials will look very similar to the Taylor polynomials, but except that it's not just involves one base point x0, but it will involve x0, x1, and so on. And it will not have a derivative, but it will have what is called a divided difference. Okay, so in particular, sort of Newton polynomials will have a form similar to sort of Taylor polynomials, right? But where we have sort of x0, x1, all the way up to xn, and what are called divided differences. Instead of derivatives. Okay. All right. So that's something which we'll see in a little bit. Okay. But for now, let's just consider the Taylor polynomial and say a little bit about that. So the first remark about Taylor polynomials are that the Pn of x interpolates f of x in the following sense, in the sense that it matches f at the point x, fx, f prime of x, all the way up to the nth derivative of f at the point x equals to x0. Okay. All right. So Pn, if you differentiate, well, if you evaluate Pn at x0, it agrees with f at x0. If you differentiate p up to n times and you evaluate x0, it will agree with the appropriate derivative of f evaluated at x0 as well. Okay, so this is one sense in which it interpolates f of x. And the second property is that there's it's a local approximation. Right, all the information is at x0. Okay. All right. So, so let's recall the error term associated with Taylor polynomials. So the error, right, has a remainder term Rn of x, which is the nth plus first derivative of f at some unknown point c, n plus 1 factorial, x minus x0 to the nth plus first, right, for c between x0 and x, some c, and f of x minus Pn of x is less than equal to m over n plus 1 factorial x minus x0 to the n plus first power, okay, where m is an upper bound, it's like to the derivative, right? For c between x0 and x. Okay, all right. So, so this is just Taylor sort of the Taylor polynomial. It's like in the sense in which it's an interpolant. An interpolant, it's like of the data, right? It interpolates. You know, it's like it's a polynomial. It's like whose value at x0 as well as its derivatives up to appropriate order, right, agree. It's like with the original function. Okay. All right. So that's one approach. And as I said, another possibility is instead of having all the data at a single point x0, you can imagine having the data at x0, x1 all the way up to xn, and that's what's going to lead to the usual type of polynomial interpolants which we talked about. And then after that, it's like we'll talk about sort of this Newton form of the interpolating polynomial, and we'll see that it gives you a way to sort of smoothly transition between the Taylor polynomial where all the data is at one point and sort of the usual interpolating polynomial where all the data points are distinct, right? And so there's a way to smoothly go between one and the other in an expression, it's like, which I said involves divided differences. And there's a sense in which divided differences are very closely related to derivatives as well, which I'll make more precise in a little bit. Okay, so let me just stop here for now.